Very good. Can you hear me? Yeah? Very good. So, yeah, small x distributions of hadrons and ions in Sartre, and we see similar pictures that we just saw in the previous talk, very nicely set up. Basically, I will talk about how Sartre is dealing with the initial state in EP and EA collisions. So the basic, how we implement these initial states in Sartre. So the heart of Sartre is the dipole model, where it's factorized amplitude, where if a photon comes in, it splits up into quark-antiquark dipole, which has a long lifetime compared to the interaction time. So you can see this as a dipole interacting with the target, and then combines into something else. And this is an example of exclusive diffraction. So I will speak about, mainly about exclusive diffraction in my talk. So this means that the target, proton or heavy ion, stays intact in the process. It's a diffraction, so it doesn't change the quantum numbers. For example, we could have a two gluon exchange that shield the color of each other. And then we have only one particle in the final state here, for example, a J psi, which will be mostly what I'm talking about here. So the good thing about exclusive diffraction is that we can measure this T, Mandelstam T variable, which is minus delta square, where delta is the momentum of this, let's call it a Pomeron exchange here. So the amplitude then splits up into three parts. We have the wave function of the incoming photon. We have the wave function of the outgoing vector meson, which is this wave overlap here. And then we have the interaction dipole cross-section, the cross-section of the dipole with the target, which is called the dipole cross-section here. And this is, if you want to have an amplitude then in delta space, in momentum space, the amplitude becomes a Fourier transform from impact parameter to momentum delta here. So this dipole cross-section is what contains basically all the QCD information that we are interested in. So if we have one two gluon exchange here, that would be this cross-section here, which is the dipole size or radius, r squared pi. Then we have the coupling alpha s, the gluon density. This is the longitudinal gluon density. And then since this is impact parameter dependent, we have this thickness function, which tells us how these gluons are distributed in transverse space. So it's actually a 3D distribution of gluons here. One is longitudinal momentum, and then we have the two transverse dimension in coordinate space, which in this picture now factorizes. And of course, the saturated version of this, which is very similar to the DBW model that Raju was talking about yesterday, we have this exponentiates. So the picture is that if we have many two gluon exchanges, this exponentiates like this. And as you see, the corresponding cross-section saturates. So for large gluon densities or large thickness or large dipole sizes R, we get saturated physics here. So this is a very good model for investigating saturation physics of the quark gluon plasma. Or they call it glass condensate is what I meant to say, but both is true. So this gives you a definition of a saturation scale, QS squared, which is 2 over RS squared, the saturation radius of the dipoles. And we get that by putting whatever is in the argument here in the exponent to 1/2. So we put all this by 1/2 and solve for R. And you should keep in mind that this mu squared, this factorization and renormalization scale, mu contains R. It's a function of R, the dipole size. So if we solve that for RS, we get the saturation scale. And roughly speaking, the saturation scale then is proportional to the thickness function. So the topic of my talk will be to talk about how this thickness function behaves in different conditions. And it's also interesting then that this thickness function has a completely different interpretation in B sat and B non-sat. In the non-saturated version, this thickness function is just the spatial distribution of the gluon wave function in the target. While in the B sat, It has more to do with the saturation scale in different positions in the target. Of course, there's no saturation scale in B non-sat. So it's interesting to keep in mind. So for B sat, then this interpretation that it's the gluon distribution in the transverse space means that the cross-section is the absolute square of a Fourier transform of the thickness function. And we can measure the T spectrum. So T is delta squared. And we can measure the T spectrum. We see that it becomes an exponential in T. That means that it's a Gaussian in delta. And the Fourier transform of a Gaussian is a Gaussian. So that means that our proton is a Gaussian in impact parameter space. Very nice. We got it. It has a width of about 4, maybe a bit more than 4, maybe, inverse GV squared. And that's it, we're done. And this, of course, is similar to DPDs, which we can measure with the EIC, which also has this kind of bell shape, Gaussian shape. So that's consistent. So, of course, I'm not done yet. We can do a lot of fun things with this thickness function. So the first thing I want to look at beyond the EP is to look at the pion cloud of protons and the pion thickness function. So in HERA, for example, we could measure the pion through so-called leading neutron events. So this are events when the proton state, it can fluctuate into different hadronic states. For example, it can fluctuate into a pi plus and a neutron state. And if we manage to probe it at that point, then we can probe this pi plus here. And then what we're actually doing is DIS on a pion instead of DIS on the proton. So we can calculate the flux factor, the flux of pions out of the proton, and then we can calculate the photon pion cross-section and then convolute the two, and we get our leading neutron cross-section for these events. And these are easy to tag because we have a very forward neutron in these events. And we can also look at exclusive diffraction in these events where we have a very forward neutron, also forward pion, a real pion, and one extra particle such as a J psi in the center part of the detector. So this we can plug into our dipole model in the same way with the proton. The difference now, of course, except for the pion flux, is also that now we have a pion dipole cross-section here. And that contains then a pion gluon density as well as a pion thickness function. So let's focus first on the gluon density. So the way we have tried to do it is to say that at small x, pions and protons, they are the same. It's just gluons at small x. And the only difference is that we have fewer gluons in the pions. So there should be some scaling factor, Rg, here. So that we can put to the test. We can calculate F2 for leading neutrons and find out what this Rg is, just making this substitution. And we find that we get a good description of F2 data in leading neutrons using Rg of 1/2. So a pion is half a proton at small x. That's very nice. And as a little aside, Arjun, which I've been doing this work together with, he did an extra study where he checked the geometric scaling of the pion leading neutron events. He found that if he plot the cross-section as a function of q squared, he get this spread in the data. But if we plot it as a function of this tau variable, which is q squared divided by the saturation scale squared, as defined by dBW, then it falls on a nice line here. So he's found that geometric scaling is there also for pions and not only for EP. That's nice to know. So let's go back to the thickness function. So there's a problem here if we want to do exclusive diffraction with the thickness function is that we don't know which function to use really, because we have two at play here. We have a pion cloud, which is described by some Yukawa distribution. This projection of the three-dimensional Yukawa into two dimensionals, which basically gives you a Bessel function K here, a thickness function, or it could be that we should use the pion thickness function. Also interesting to keep in mind that the T-spectrum of the proton then should be, the slope is proportional to the target size squared. So in this case, we would get a larger slope, the T slope, and in this case, we could get a smaller T slope because the pion should be smaller than the proton. So the way to get around this is to realize that this cross-section, which is proportional to the amplitude squared, absolute squared, it's actually averaged of the position of the pion, of the virtual pion inside of this cloud. So we can rewrite this a bit to say that we have the second moment is actually, we can add and subtract the first moment of the amplitude squared and arrange the terms in this way. So you see that the first moment of the amplitude with respect to pion position would give you the average pion position. That should be given by the Yukawa potential, the pion cloud around the proton. And then this term here is the fluctuations in the pion position from event to event. That, of course, is given by the pseudo-real or almost real pion inside of the pion cloud. So that is given by this Gaussian distribution of the pion thickness. So we should then expect to get two slopes out of this. One steep slope from the pion cloud, and then which given by the first term, and then a more shallow slope given by this smaller pion inside of the cloud. And we put this into our calculations, and this blue line here is from the pion cloud, and this red line comes from the fluctuations of the pion position inside of the cloud, and we add them together, and we see that we get a perfectly nice line here. So this is a prediction for what we could see, for example, at Hera or the EIC. And we see that it looks like it's one slope, but it's actually a combination of two slopes. Here we use the size of the pion as 2 inverse GV squared plus minus 0.5. Kind of an educated guess, since there's no real measurement of that yet. And this is for raw production. We see maybe a little bit more of a hint of two slopes here, but it's not very clear here either. But anyway, we can use the thickness function in this way to make predictions about the pion leading neutron events at EIC and at Hera. So the next thing I want to talk about is the nucleus thickness function. So the naive way to go about that is to replace the proton thickness by the Wood-Saxon distribution. Well, the two-dimensional projection of the three-dimensional Wood-Saxon distribution. And then replace the gluons by the nuclear PDF gluons, and that should work perfectly fine. But there is a problem here is that we know that in heavy ion collisions, we have two kinds of distributions. We have coherent and incoherent events. The coherent events is what I talked about so far. The target stays intact, and we coherently probe the entire target in the event, and we get one extra little shape psi out of it or something like that. But then we also have incoherent diffraction. And these are the events where the target gets excited, and then it de-excites afterwards, usually by emitting one or several neutrons, or it could break up into fragments, or it could emit alpha or photons or whatever. So it gets excited is the thing. So it's a different final state than the initial state. So in the good Walker picture, this can be easily understood. So if you have the incoherent cross-section is the amplitude absolute squared. For the case when the final state is not equal to the initial state, we get this sum over all possible final states. We can add the point where the initial state is equal to the final state and subtract it again. That completes this set quantum mechanically. And then we get the second moment of the amplitude minus the square of the first moment of the amplitude, very similar to what we had in the pion case, but the difference now is, of course, that we have a different final state. than in the coherent case. So this again gives you a variance of the amplitude. So the fluctuations of the amplitude is directly proportional to the incoherent. So we can probe two things here. We can probe the size of the nucleus through coherent scattering, and we can probe the fluctuations at different scales in T through the incoherent diffraction. So, but that, of course, we can't do with the Woods-Saxon picture. So we have to go to a Glauber picture where the nucleus is a collection of nucleons, and the non-scattering amplitude of a heavy nucleus is the product of the non-scattering amplitude of all the individual nucleons. So the probability of not scattering with the nucleus is the product of not scattering with any of the nucleons. And then we can express this in terms of the cross-section then. So this product inside of the dipole cross-section becomes, well, it exponentiates here. So the product becomes a sum. So now we have the thickness function become a sum over the proton thickness functions taken at different b's. And this bi here, we distribute then the nucleons according to the Woods-Saxon distribution. So, and then we don't need nuclear PDFs anymore. We use the proton PDF for the longitudinal gluon. So that picture is very good because then we can get, if you look at T is equal to 0, we have the Woods-Saxon nucleus, and then we can get the Glauber nucleus at larger T. And of course, this is one configuration. To get these cross sections, we have to average over all possible initial states, all possible initial state configurations. And then we can model these coherent events as well as the incoherent events, which is plot I guess you've seen many times. It's in the EIC white paper, for example. So the thing is that in EP, the proton can also break up sometimes. We can have incoherent scattering in protons, which is called dissociative proton events. So Heikki Mäntysaari and Björn Schenke, they introduced this hotspot model where the proton now is not just a Gaussian, a spherical Gaussian, but it's now a collection of hotspots. So they choose as a standard 3 hotspots. That corresponds to that we have 3 valence quarks, very fast valence quarks, where which radiates this, act as sources basically to the gluons at small x. So the large x valence quark are the sources of the small x gluons. And then we have a spatial correlation between the original valence quarks and the small x v gluons here. So that means that the thickness function of the proton becomes a sum of thickness functions of hotspots, very much the same way as we did with the collection of nucleons instead of the nucleus. And with that, you can describe this incoherent diffraction on the proton very nicely. So this then gives you the right amount of fluctuations if you tune your parameters correctly. And we can implement that in Sartre for EA, which we have done. We see that this plot, for example, the Alice incoherent data got, of course, improved when we added more fluctuations. And these fluctuations become important for T larger than 0.2 GeV squared. And we see that this star T spectrum, well, it's T squared of the vector meson, but that's basically the T spectrum, works well up to at least 0.1 GeV squared here. So we have a whole part of the spectrum which can be well described with these subnucleon fluctuations. All right, let's go back to the proton thickness. So I said that we just measure the T spectrum of the proton and we get an exponential, and Bob's your uncle, we have our proton. However, it's not so simple. It turns out that if we measure this T spectrum at different values of W, we get different slopes of the spectrum. And if you extract the slopes as a function of W, you see this H1 and Zeus data, they kind of look like there's a growing trend here, that this proton gets larger with W. The data is, of course, large arrow bars, and the Zeus on H1 seems to have some tension here. But anyway, that seems to be the trend here. So that we can incorporate into the proton thickness. So we can turn Tp of B into T of B and X. We can add an X dependence of the proton thickness so that the X and impact parameter don't factorize anymore in the dipole cross-section. And one way to do it is just to let this size of the proton vary with X. This would be one simple parameterization to do that. Of course, we want the proton to get larger for small x, because small x corresponds to large W, and vice versa. We see that we get a good fit with the small negative value of this lambda p here, which gives you the behavior we want. Then we can describe the data. So the black lines here is with the varying width of the proton, and the dotted lines are without it. So we see that we can better describe the data in this way. Of course, we also want to look at incoherent events at different energies. So we need to also look at the hotspot model. So we revisit the hotspot model as well and add a X dependence. So there are two prescriptions to do that. Either we let the width of the individual hotspots get larger when we vary X. That also means that the normalization of the hotspots stays the same, right? The thickness function is a normalized function. So if we make the hotspots wider, it means that they also get less hot because they spread the normalization into a larger region. And we see that then the proton grows a little bit with the hotspot width here. Another way to do it is to add more hotspots at smaller x. So we get like kind of a step function, which is parameterized like this. So if we get to smaller x, we get more and more hotspots. So if you see the energy going in this way, in this case, the hotspots we get larger and larger, and at some point they will start to overlap. And here we get more and more hotspots, and again, at some point they will start to overlap. So we would get similar physics out of these two prescriptions. So if we compare that with the B slope of the spectrum, so here's the black line. This is where the hotspots are getting wider. It can incorporate this quite well, this growing B slope. This blue dotted line here is the one where the proton as a whole grows without any hotspots inside of it, no substructure. And also encapsulate this fairly well. It's a bit lower, but yeah, maybe the black curve is better, but who's to say? And then this red curve here is when we vary the number of hotspots inside of the proton. And we see that this doesn't really do anything in this range of W because, you know, we need to go to high W values until we get the next hotspot arriving. So that seems to not really do well with this data. So we wanted to do incoherent diffraction in EP and look at how that varies with energy, W. So this line here is with no variation, and these black line and red lines are as before, with the hotspot size variation is the black line, and the number variation is the red line. We see that they can seem to turn over here. So at large W, we get a big suppression due to the difference at different x between the blue line and the black and red lines here. But there's no data in this region, so we can't really tell if this is actually the physics that is happening or not. And also the inelastic to elastic ratio shows this big suppression of incoherent events at small x at large W. So potentially this can be measured at LHC at ultraperipheral collisions, but they haven't really managed to do it yet. But they say that they will do it in the next few years. Skip that. So the next thing I want to talk about is large Mandelstam T variables. So the hotspot model, of course, is a non-perturbative phenomenology. So it's only valid for small t, really. Smaller than 1 GV squared or so. But we have data from Hera, which goes up to 30 GeV squared. It's from H1, and this is from Zeus, and they have measured the exclusive diffractive T spectrum to very large T here. So that would be nice if we could incorporate that into our thickness function and describe this data as well. So in order to do that, we have to make the thickness function dependent on T. So there's a few hints we get in order to think about this, on how to proceed to incorporate that into a model. One is that we have done some earlier studies where we can describe this T spectrum with a sort of self-similar structure of hotspots within hotspots, kind of a it's a self-similar gluon structure here. And we see that in the way the parameters falls on a line here on a log scale. And another insight is this recent PRL, where they show that if they look at the final state hadron correlations in DIS at small x, they see that the result is consistent with a maximally entangled state. So they get maximum entropy in the correlations. And from von Neumann entropy, that tells you that we have an entangled state, maximally entangled state at small x. So the small x partons are maximally entangled, which you can see as they are described by the same wave function. So I don't know how important that is for our study, but it helps us think about how the small x gluons behave here. This suggests that we can describe the hotspots T spectrum with a linear self-independent evolution, scale-independent evolution. This scaling behavior shows us that. And so what we talk about is that we let the Pomeron here act as a probe. And the resolution of the probe is 1 over T in space. So the areal resolution is 1 over T. So that means that if we make a measurement in one event at a value T, that means that we probe an area of 1 over T. So that means that this collective wave function collapses into this area of 1 over T. So that means also if we change T, that acts like if we go to a larger value of T, smaller probe, that means that would manifest as a hotspot at one value of T splitting into smaller hotspot at another value of T. So that is what we try to model. So we have suggested a hotspot evolution model where we consider a parton shower-like evolution of the resolutions in the resolution scale of the number of hotspots in the proton. So a hotspot might split into 2 hotspots, and we suggest a very simple splitting function. We would like to be able to calculate this from first principle, but we haven't managed yet. But it must look something like this, whatever comes out of it. That's the right scaling behavior, and it behaves nicely probabilistically. And of course, if we want to get a splitting at a value T, we need to multiply the probability of it splitting at T with the probability of it not splitting before this value of T in our evolution. If we evolve from value T1 to T2 and want to have a splitting at T2, we have to multiply the probability of splitting at T2 with the probability of it not splitting between T1 and T2. So this is this Sudakov term here, and this gives us a probability density for hotspot splittings like this. So it looks like this for different values of T. You see that we get an exponential decrease here. Well, it goes like 1 over T, of course. The density goes like 1 over T. So the idea is that we generate the 2 offspring hotspots from the thickness of the parent hotspot. We conserve the normalization in each splitting, and then we calculate the distance between the generated hotspots and give them a width of 1 over T. And then we see, are they resolved? So if the distance is larger than either 2 over delta or larger than 2 times square root of B, which in this case is exactly the same, then we resolve it and we keep it. If the distance is smaller than this, then we can't resolve the splitting and we reject it. So this effectively gives us a repulsion of the hotspots. If they are too close, they cannot exist. So that means that we generate a little bit hotspots which are a little bit apart. So that naturally falls out of our resolution picture a little bit of a hotspot repulsion, which has been suggested by some groups to solve some problems in flow dynamics, for example, in the initial state. So we can implement this. We have only one parameter here, alpha, which we can fit to the data. And then we can get a nice description of the entire T spectrum here. So I think that's the strength of this model, is that it doesn't contain many parameters, just the one parameter, and it gives you, well, it has, the initial state has a lot of parameters, but that we have already described. So we get all this extra physics of larger T for the price of one parameter. So then our thickness function has now become not only a function of impact parameter, but also impact parameter and resolution T here in this scale. So you see at different T values, we get a more complicated structure in the proton. So these are very similar to the plots that Olga showed in the last talk that Björn Schenke had created from the colloid glass condensate. So it behaves very similar to those. So to finish up, I thought I just return to this notion that the saturation scale, so if you look at this, we have both B sat and B non-sat here, and these two curves are on top of each other. So at this values of W and Q squared, we don't seem to have any saturation in this spectrum. So I talked to you about that, how the thickness function have different interpretations in the B sat and B non-sat. That's not really relevant here because they're on top of each other. So let's return to the notion that the saturation scale is roughly proportional to the thickness function and see how does it behave now at different scales of the T spectrum in what I've talked about so far. So here in the Wood-Saxon distribution, we see that we have a maximum thickness about 10 to minus 1, which is in this region here. If I add the collection of nucleons to that, we see that we get some spots here which are hotter. So this will, of course, vary from event to event, where and how hot these spots get, because this is the projection of the 3D nucleus into 2 dimensions, remember? And we see that we get a factor of 2 larger maximum thickness in some points here in the transfer space. Then we can go to the hotspot model. So then we see that the enhancement in some points here have grown by a factor of 6 compared to the Wood-Saxon. And if we go to even larger scales, even smaller hotspots, we have gained an order of magnitude. Of course, what's also happening is that we get holes, right? We get cold spots. Whenever we get a hotspot, we also get a cold spot, right? The total normalization stays the same, but we get strong saturation scale fluctuations inside of the nucleus this way. And that seems to, I don't know, we have to look more in detail. So that takes me to my summary, which is a poster in this case. So we started with the thickness function of the proton. We used the same machinery to describe the leading neutron pions, which had these 2 slopes, one from the Yukawa and one from the pion potentials. That gives us this T spectrum, the prediction. Of course, it would be nice to also investigate how this behaves for EA. We haven't done that yet. Maybe this could be an interesting thing for EIC to study, both in EP and EA. So in EA, we can just change the thickness function into a collection of nucleons, and we can describe the EA physics quite nicely in exclusive diffraction. We can add substructure to the nucleons that enables us to look at dissociative protons very nicely. And we can add a x-dependence to our thickness function that will give us the change in the T-slope. So basically the change in the size of the proton in a nice way, which also we would like to study. We actually are studying it right now, how this affects the nuclei. So that's something we're looking for UPC in. And then we can describe the entire T spectrum by adding a T dependence to our thickness function. And again, that would be nice to study in heavy nuclei. And also what we want to do is combine all of these processes, which I described now, all these pieces, we should implement them all into the Sartre event generator. So far we have this piece in, and this piece in, and this piece in, but not these three. So those would be very nice to add and combine into a more inclusive, exclusive diffraction generator. Yeah, and of course, all of this can be measured at EIC. I don't know, I keep pushing people into telling me study how far in T we can actually go in exclusive diffraction at the EIC. I think last time I asked, there were really no studies on this. That would be very interesting because that contains very compelling physics, I think, the large T part, exclusive diffraction, both in EP and EA, because that would be a nice probe of the fluctuations of the saturation scale. All right, thanks.
Great, thanks a lot for the nice talk. We have some time for questions.
I have a couple of questions. One, if you go back to the previous slide, Tobias, so one question was, if you have some X dependence in the T functions, does this violate your initial sort of assumption that you had this factorization of the PDF times this T function?
No, it doesn't. It just tells us that at different X, the longitudinal gluons are distributed differently in transverse. It doesn't really violate.
So you don't need to model at the same time the X dependence and B dependence at once.
We always keep this thickness function normalized.
Ah, okay. And also the other question is, you are using Gaussians and possibly shifted Gaussians with this hotspot model, but why only Gaussian and not weighted Gaussians or power law?
That's an excellent question. So we're looking at Fourier transform hairs, and of course they are very sensitive to the tails of whatever distribution we choose. So yeah, we are looking into different. We also, yeah, we're looking into different ways to look at the shapes of the. For example, I think a more realistic shape might actually be a Laplacian for the hotspots. So that is something we are looking into.
Okay, any other questions? Maybe let me ask one quick question. At the beginning you mentioned, I think, that the pion and the proton at small x differ by a factor of 2 or something.
Yeah.
What is the intuition behind that factor of 2?
Okay, so the intuition, the factor 2, don't have a clear intuition about. I mean, I don't know what you would have guessed, but yeah.
Right, but if it's like an exact factor of 2,
this was a fit we did.
Okay, so fit value.
But it seems to be a factor 2. So the structure is very different, right? We have 3-valence quark with the gluon field inside of it versus quark and an anti-quark with a gluon field in between. So I don't think I would be able to guess really some factor different there.
Okay, any last question? Otherwise we'll, right, then let's thank Tobias one more time.
Thank you.